I can pick up if you cut out.
Yeah, I wrote it down too, so. Are we good to start? Okay, all right. Hello, ladies and gentlemen. Welcome to day 2 of the 2020 summer series. I'm Connor Martindale, a mentor with the Robot Dolphins. And today we're going to be starting off with the scouting and strategy panel brought to you by Team 5199. Following this panel, which will end at 5:40, we will have a presentation on machining with teams 3476 Code Orange and the Robot Dolphins. They'll be covering the various ways they incorporate CNC milling and routing into their builds. The machining presentation will run until 6:25, and at 6:30, experts from Team 3309, Firebots, are going to be ending out the day with a presentation on the uses of fasteners in FRC. In case you missed us yesterday, the way this works is that during this panel, we ask that if you have any questions about scouting, match strategy, or season strategies, to please post them in the YouTube chat so that our experts can get to your questions right away during the presentation. While you're all typing your questions, let's get started with some introductions for our panelists. Take it away, Teddy.
Of course, I'm muted. Hi, I'm Teddy Bullicus, a strategy and scouting mentor, as well as the former drive coach for Robot Dolphins. My team calls me Stratmaster, but you may know me as a skinny 7-foot legend that wears zip ties on his safety glasses and tears off his pants to reveal stylish short shorts at competitions.
Hi, I'm Ollie Aruji, the strategy lead on Team 5199 for the upcoming year, as well as the team president.
Hi, I'm Caden Davis, the current scouting lead for 5199. I've been learning under Connor and Teddy for a few years now, and I'm always seen at competitions with a clipboard or on a phone call.
All right, and those are our panelists. So while we wait for you guys to type your questions into the YouTube chat, we're going to go ahead and get started with some questions that we organized beforehand. So first of all, I'm going to come to Ali with this first question. In terms of your overall season strategy, how do you balance between your strategy team and your design team throughout the season, and especially at kickoff?
So for our team as a whole, as you know, strategy and design play hand in hand with each other. At the beginning on kickoff day and just that first week in general, our whole strategy team and our whole team in general is just constantly going through the game manual, constantly reading everything and watching the match videos and pretty much trying to put together what we want our goals to be for the season. We, like many other teams, create a want, need, and desire kind of column for each of the things that we'll need in a robot for the whole season. And that plays a lot of the role in how we end up designing the robot. We always want to prioritize what scores the most points, and as a strategy team, that's what most of our work is going into a new season. Identifying what we want to devote our time and energy to, and what's going to have the most benefit for us as a whole. Like the past couple of years, we've always been emphasizing on the end game because we've identified that that's like the easiest, most consistent ways to get a lot of points. And because of that, we always make sure we put extra effort into our climbers. And a lot of the design and strategy talk that you were talking about comes in the weeks like 2 and 3 of the season when we're working a lot on prototyping and starting up the CAD. Our strategy members are pretty much always on the shop, always being asked questions, and that kind of leads us to success later on in the season with our robot design.
Alrighty.
To expand on that a little bit, one of the main things that we do as a strategy team is we kind of compare the point scoring and the difficulty of each task in game to try and preemptively figure out how we think the game is going to be played. Like in our current game, Infinite Recharge, you guys remember that the color wheel wasn't really a major factor. We kind of determined that before the season, and in doing so, we didn't devote that much time or resources to making a color wheel manipulator. So we focused on what would be most helpful for our robot.
And to kind of give another example, 2019, we kind of had a similar approach. We knew that picking up and cargo and hatch panels were going to be really, really important for the speed of the game and the amount of points we scored. Because of that, we made sure to devote a lot of time onto the pickup mechanisms, especially, to make sure we can have a good basis to go forwards in the remainder of the season.
Alrighty, so now we have our first question from the chat from Rick and Ali. How much time do you dedicate to drive practice versus optimizing your robot? Where's your cutoff point?
So pretty much for us, ideally we'd want to give at least 2 weeks at the end of the season to work purely on the robot to just start drive practice. Because it's really, really important for us for drivers to be comfortable with the robot. Although they do have practice using like the off-season robot, driving that around, even while we're in season, it's a completely different situation to be on the robot that you will be using on competitions. The past 3 years, what we've been doing to kind of compromise on this matter a little bit more is to create a practice robot to use purely for driving practice for our driver, especially when bag day was a thing. And even now that bag days got taken away, this is the same thing we did this year to make sure that we don't really wear down our actual competition robot too much. But for us, again, it comes down to the season, comes down to how many things there are to juggle, but overall we prioritize driving very, very greatly, although it doesn't always end up that way.
Alrighty, and I have another question, this time for Caden. How do you decide between wants and needs on the robot?
So this kind of comes back to what I was talking about before with comparing like the reward versus the effort of completing certain tasks. We use that info to determine what we need to have if we want to stay at a competitive level. As Ali said, during 2019, we determined that being able to do both hatches and balls was necessary for competitive robot. So we put that in need. We determined that having a consistent climber, because the end game was worth so many points, would go in need, but having a fast climber, which would be very nice and would make us a lot better, it wasn't really necessary. So we put that under want. So we kind of rank it like that. Like, if we need this to be a competitive robot, it goes under need. If it would help us to be a competitive robot, it goes under want.
Alrighty, thank you. And as more people are joining in, if you have any questions at home that you would like to ask any of the people currently on, make sure to comment them down below so we can answer them. So now we have a question for Ali. How do you prepare for an alliance meeting before a match?
So what we tend to do ourselves as a team is our drive coach, probably one other member of the strategy team, as well as our driver, would always, well before the match would start, go over and talk with the other two alliances. We'd send a representative, designate a meeting place at one of our pits, and have all the team strategy individuals come over and talk. During that meeting, a lot of strategy is involved, and we usually like to take the lead in it. This past year, we had whiteboards that I highly recommend you have with the field map on them. And what we use those for is to designate where we start, where we're going, and to kind of designate different zones for each team. Because in the past, especially 2019, we had issues with robots interfering, robots bumping in and kind of like defending our own team. And because of that, we like the method of using different zones, and that would allow the different robots in charge of that zone to score and defend in that particular area. And that would kind of lead to success later on. And additionally, we'd also kind of talk amongst ourselves to see who's like the best scorer and best robot on that area, on our alliance, and kind of play around that. But also a big part is talk about the opposing alliance. Caden can give a bit more info on how we use data to kind of manage what we do and how big of a role like defense or our aggression kind of varies based on the other team.
So when we gather data from our stand scouts, one of the most important things for the strategy team is just the most basic, simple statements about the other robots on the team for the alliance that we play against or are playing with in the next match. For example, the robot broke, it caught on fire, it started smoking. Something like that is critical information that is conveyed really simply from our stand scouts. Stand scout data can also tell you important things like, oh, the next team is one main scoring robot who is seated second and has been having the highest point output, and then 2 defense bots that aren't extremely effective. Then we could know from that where to put our defense bot, and we would naturally put it on that very high scoring enemy robot. So just even the most simple stuff, such as defense, quality of robots, and who is able to do what, is very important data that you can get from your stand scouts.
And a big role that the drive coach has in all of this is making sure that whatever's talked about in the meeting beforehand continues throughout the whole match. A lot of times when you're on the stage and playing the match out, teams tend to forget what was discussed beforehand. So usually our drive coach does a really good job in making sure that other teams stay with a plan and kind of have a strategy moving forward.
All right, so our next question is coming from Eli Uva in the YouTube chat, and he asks, how do you go about picking your drive team? So Teddy, as a previous drive coach, why don't you go into the idea that we have behind that a little bit for us?
Alrighty. So our general philosophy is, first of all, you need a drive coach, because the drive coach is kind of like the glue that holds the whole thing together. Because in general, the way we see our drive team is, I'm not muted, right? Okay, cool. So we have the drive coach, and they are the ones, the voice that the operator and the driver listen to on the field. Because in past years, we had issues where we were the coach said one thing, and there was so much noise that the driver didn't do that, and it cost us some points and possibly the match. So we try and emphasize that the drive coach is the main body in the main vessel of voice for the drive team. And so that usually goes to a position of someone who knows the strategy, someone who's been on the strategy team for several years, like myself or Connor or some of my other panelists like Oli. And then from there, we don't go strictly based off skill. We go more off dedication. Like if you're in the shop, 40 hours a week, you're there every day, you're building the robot, then you should have the chance to drive the robot at competitions. If you go in maybe once or twice in the season, and then you show up the week before a competition and say, hey, I'd like to try and drive the robot at the competition, that's not exactly the best way to go about it, because you need to have time to train them. And same thing with the operator. Usually we have someone on the operator who mainly the intake in main intake games like in 2018 and 2019, where it's very centered around the intake and not so much as like passing things through the robot like in 2020. So people who work on the intake more know more about it and are able to work with it more. So generally that's how we do it. And when you have a drive team, you always have to have a programmer. And if the driver and the operator and neither of them are programmers, that's how we fill our technician. Because if there's any type of software problem, you got to have a technician, got to have a programmer. In this case, in our case, usually the technician to help solve those problems. So next, we have a question from Terry Wells that says, what specific steps do you follow to convert the game manual into a well-considered strategy? You mentioned discussions and need, want, desire, but we struggle taking the next step to final strategy. So Connor, would you like to offer some input on that?
Yeah, so obviously it all starts off on kickoff day when you get access to the game manual, right? So the first thing that we all do as a team is read through the game manual together. We use, I can't remember what their number is off the top of my head, but this year we started using another team's, what is it called? I think it's like the game manual quiz or something. So we all had everybody go through the rule manual together. Then we all went through the quiz together to make sure there wasn't anything that, people were confused about or that people just missed, or even that our whole team missed. So that definitely helps us all kind of be on the same page. In terms of going into a well-considered strategy from then on, our whole strategy doesn't do a whole lot at the beginning, aside from our robot design strategy in terms of like match play. We usually try to start covering that once we get closer to the season starting, once we start knowing what our robot is actually going to be able to do. As for the needs, wants, and desires, that's a really good plan that we use for just kind of signaling out, okay, do we want rank points or do we want normal points in order to win the match? Do we want to climb or do we want to score more points? Like, which things do we want to focus on? And then we kind of just all talk about it as a team until we eventually come up with something that, one, we all agree on, and two, we think from a design philosophy is actually going to be possible for us to do. And then as for taking the next step to final strategy, I would say that it really just comes down to seeing what can your robot do? You know, once it's all said and done and you've built it, what can you do? What do you struggle with? What do you need help with? And that really gives us kind of our, I guess, plan once we go into matches of what we want to do, what we want our alliance partners to do, what we don't want our opposing alliance to do, all that kind of stuff.
Oh, just one thing I want to add for that. Be realistic with yourself and your alliance about what your robot is capable of. Because a lot of the times, just being able to like know for sure that you can do something rather than, oh, we scored 10 points one time in practice, but we've been averaging around 6. Say you've been averaging around 6 so you can play around what your team does like well. Because you don't want to go in with a series of expectations for a match and then have it all like crash because it wasn't as realistic as it could have been. Because no one's going to be mad at you for not having a robot that can do everything, as long as they know what it can do and you can work around that. It's a lot of like resource management when it comes to creating your strategy for a match.
As an example of that, at Del Mar this year, our shooter wasn't working 100% how we wanted it to. So we didn't go in saying like, oh yeah, we're going to score, 30 balls and then have an amazing auton, climb, win every match. We're telling our alliance partners, we don't know. So they knew that it's kind of to plan for it. It's not that way. They're not banking on something that we don't even have faith in. So we want to like have a alley of trust between each other. Like, okay, yeah, we know for sure this is going to work. And then this part is a little iffy. So now we have another question from Angel. Do any of your teams use an app to record data for the scouts, Caden?
So in previous years, we have done this paper and pencil, having students fill out scouting sheets and then put those into a big binder. This year, though, we transitioned to electronic scouting. We didn't use a specific like custom app for scouting. We made a Google form that students could fill out on their phones, though. For setting up that Google form, one of the nice things about it is that it has very easy integration with Microsoft Excel. Microsoft Excel. So from there, you can do a lot of advanced kind of data processing, I'd say, on all the input that you gather, and that can help you glean further insights. And that's kind of why we made the switch.
All right.
Go ahead, Teddy. Yeah.
Make sure to comment your questions below if you have any. Connor?
What Caden was saying real quick, I had some trouble unmuting my mic for a second, so I wasn't able to jump right in there. But again, with this year, as Caden mentioned, we just started going to like fully digital, which I think overall was a pretty big success. And we really liked the way it worked out because it really forced us to kind of focus on, okay, what do we actually want to record? Because when you're doing it on Google Forms, there's a lot that you're not really able to, when you're doing it on Google Forms, there's not, oh my goodness. There's a lot that you're not actually able to record as if you were on pen and paper. For example, what we used to do is we used to draw out the robot that you're scouting, their path, so that when it came to playoffs, you'd be able to see, okay, where do they like to play the game? Like, do they like to play on the far side, the close side, in the middle of the arena, stuff like that. And it really forced us to say, okay, do we actually need that information? Are we actually looking at that? The short answer is no, we weren't. And a lot of our scouts are kind of frustrated with having to do it. So they were really thankful that they didn't have to do that anymore. So a big part of the online thing that we use, and something that Google Forms is really nice about, is that it's so simple and it is a little bit limited, but it really forces you to think about, okay, what do we actually want and what do we need to look at during the competition? Our next question is going to be coming from the YouTube chat as well. This is from Jay Bullock, who says, how do you decide your pick list for playoffs? So Caden, why don't you start us off with this one? Caden, you're muted, yeah.
Yeah. I start trying to form my pick list towards the end of the first day of qualifiers, and that gives you the entire second day to kind of refine your choices. But usually with the pick list, if you start it at the end of the first day, you are able to meet with kind of the rest of the strategy team and the other scouts to get input on that pick list. In terms of actually deciding where robots should go on that pick list, you kind of consider what robots would be able to be on a team with you without interfering with your gameplay, and that would complement your gameplay. For an example, as Teddy said earlier, during Del Mar, our shooter was not very functional. So we made it a priority that our first pick was a robot that excelled in that department so that they could kind of make up for our shortcoming there. Also, we wanted a robot that could climb with us without interfering with us. Then for your second pick, you have a bit more limited of a selection, but what you want to try to do is to shore up any kind of gaps in the team. Like, let's say your robot can climb, but your first pick, even though they're really good, they can't climb. Then it would probably be optimal for your second pick to be able to climb. So you kind of have to analyze it not only as just, here is the first pick I want, here is the second pick I want. You have to consider, if I have this first pick, what second pick robot would kind of complement that team? And all of this kind of applies even if you aren't in the top 8. Like, let's say you are the first pick, then you are still needed to share that data with the first pick, or with the captain team, on how to choose a second pick that would complement both of you guys.
Like Caden was saying, a lot of that also depends on like the game. Like for 2020, for example, you really don't want to have like 3 tall robots, because if that happens, you won't really end up using your trench run at all, which is one of the most valuable like zones in the whole game. Because of that, it's really nice to have at least 1 trench bot or even 2 to be able to maneuver in that zone. Or like looking at 2018, for example, some would be like, oh, we don't need our third robot to be able to do the scale at all. But in some areas, teams identified that like the top teams were so strong in the scale that in the Auton that they wouldn't really be able to do anything. Because of that, what we ended up doing at Worlds was we had all 3 of our robots at the very beginning of the match immediately do the scale. Doing that allowed us to kind of offset the Auton balance and actually have us winning on that front. Because of that, it's really, really important to have that idea in your head before you go in, because otherwise that position would never be able to happen, and you would never be able to win that match if the robots just weren't able to do what you needed them to do. So you just really need to like think in advance in that regards.
Yeah, a huge part of making the pick list is just making sure that everybody's involved, because some issues that we had in the past, like for example, when I was first starting on the team, I was kind of the only person involved with our scouting and like our pick list, and it just kind of all fell on one person. So it was really hard to get a big picture of the event, whereas what we're doing now is we're having all of our scouters. We have 2 scouting leads, and Caden, for example, takes the primary responsibility for making the pick list, but we have another scouting lead who helps him with that. And all of our scouts are giving input. Our drive coach is giving input. Our drive team is giving input. Anybody who saw anything is giving input to just kind of make sure that we actually are seeing everything from every angle instead of getting the limited perspective of one person. And I'll speak from experience in saying that doing it yourself is a really bad idea. You make mistakes. I made a lot of really bad mistakes in some of the teams that I picked. We ended up having a lot of fun and still doing well, but I definitely got some questions afterwards like, hey, why'd you pick that team? And I realized, oh yeah, there were better options. But so yeah, just try to be involved with the rest of your team as much as you can, and just make it a whole like team effort. Even try talking to the teams that you want to pick. Just say, hey, if we were to pick you guys, A, would you say yes? B, is there another team that you'd want to work with? Why would you want to work with them? Stuff like that. So just reach out to other people. Our next question comes from Tiara, who says, how often do you switch out scouts during your competition? So Ollie, I'll give you this one first.
So yeah, a big thing that we do is we have one scout for each of the robots on the field. This is a way we do to keep track, and so this is how we kind of base what scout does what robot, because I know a lot of teams get confused when that comes up. We assign based off the starting positions. So each of the scouts is assigned to a starting position on the field, whether it's a red 1, red 2, red 3, blue 1, blue 2, blue 3. And how we do that is from then on, we tend on, depending on how many people we have at the event, we kind of shuffle through everyone to make sure everyone gets a break. And we don't want to make it like a drooling task on anyone in particular. And we also sometimes switch out people going on pit scouting runs or staying on sand scout to kind of like make sure it doesn't become a too repetitive and a grueling of a task, because we really rely on our scouters as a team, and we want to make sure that they are all like more or less like happy with doing what they're doing. Caden, if you have anything else to add on that.
To kind of add on to how to make the scouts kind of enjoy scouting, is you want scouting to almost feel secondary to actually watching the game. They should not be spending the entire time frantically writing, but they should just write down like key input, key factors that will help us like actually with our data. One way I've personally found to get scouts more engaged is when you collect your scouting sheet, or now this year when everyone submits, I just have them tell me in one like brief sentence how the robot did. Like, all right, cool. How did the robot do? And they will respond with something like, it broke, it stayed on the platform the whole time. Or they could respond, it scored 8 balls, it was really fast, and the drivers looked really competent. Just something like that, directly communicating with one of the leads lets them really feel like what they're doing is actually being valued and actually contributing to the team's decisions and the team's success. Just to make it feel like they aren't wasting their time with it.
Alrighty. So if you have any questions during this stream, make sure to comment them down below. We have another stream question here from Suvan. How would you set expectations that challenge the team, but also are realistic? Ollie?
So that was a thing we actually like kind of struggled with this past season, 2020. Going into the season, we were like, okay, we're going to do a tall robot. It seems to be the easier option. It seems to be the more reliable and consistent one. And we were like, it'll do good enough to be competitive. As we saw a lot of highly competitive tall robots we're seeing at different competitions in the 2 weeks that we had competitions. But kind of 2 weeks, 3 weeks into the season, we started having a lot of conversation on the topic of, should we go tall or should we go trench? And that eventually made us completely switch 360 on that, with everyone unanimously agreeing on switching over to doing a trench bot. That would be far more difficult. Having to have more accurate like spacing or hopper design and all that would have to be completely changed. But we agreed to go for the leap because we decided that the benefits of going trench would far outweigh the cons of doing it. Being able to do just constant runs under the trench would be able to prevent any defense from being able to kind of shut us down. We saw a lot of teams in 2019. They did great like the first 4 weeks of competitions. But then like week 5 and 6, and even at Worlds, they were having a lot of issues because they weren't used to playing around defense, like high caliber defense robots. And that's what we wanted to make sure not to happen, especially with the climb zone having those 1-inch bumps off the ground. We want to make sure there's no tipping, there's no issues with any of that. So just doing a trench run for us was worth the risk. And even though we cut it very close with our timing, I think we're all happy that we went with that decision.
Yeah, so that decision ended up being something that, as Oli mentioned, was something that was really heavily debated for those first couple of weeks. And the expectation we set at the beginning of the build season was that, okay, we're going to have a tall robot. We're going to be done building it like week 4, something crazy like that. And then we're going to have a ton of drive practice. Like we're just going to be super on top of everything, going really fast. And then that decision to switch over when we realized from a design and strategy perspective, not only could we do it, but also that we wanted to do it, was something that really made this year challenging for our team. And looking back on it, we probably we were right up to the wire with finishing our robot, and we had a lot of issues at our first competition. So looking back on it, we probably wouldn't want to do something like that in the future and set, like you're mentioning in the question, an expectation that's a little bit more realistic, because switching your entire robot design like 2-3 weeks in or whatever it ended up being was a huge strain on our team. And it was a really rough time trying to get that together. So we really, this year, at least, especially this year with the modified game rules, we're going to be definitely trying to do something that we can really see, okay, even if we do need to change it, we can still make this plan work. I believe that's it for our YouTube questions right now. So we're going to go ahead and head back to our questions that we have prepared already. So again, if you have any questions for any of our panelists, please put them in the YouTube chat. We'll be here for about another 9 minutes before we start getting ready with the next panel. So without further ado, Caden, I'm going to ask you to talk to us a little about how our scouting system works. Explain to us kind of what we do for scouting, what we've maybe tried in the past, what you like about what we're currently doing, any advice you have in terms of creating your scouting system.
So we kind of divided scouting into two main groups, our pit scouts and our stand scouts. They're largely the same people, but we kind of use pit scouting as a way to get people out of the stands, just as a break almost. Granted, pit scouting is still very important, but pit scouting is most beneficial for finding major flaws in certain teams' robots that help us be better prepared, like knowing a robot just can't shoot into high goal. Well, we kind of use stand scouting for measuring the robot's actual in-match performance. For our scouting system, we try to make it a mix of qualitative and quantitative data. So for qualitative, we could be just how skilled were their drivers? Did they have efficient routing and scoring? Well, quantitative would be something like how many power cells did they score? We kind of funnel all of this data first into the scouting lead, and then that data is communicated to our coach and strategy team. In terms of what we choose to track, we kind of shift it throughout the season. Like last year, we had a different scouting sheet for each competition. We try to focus our questions so that we can get a more complete picture of robot performance than you could get just from the numbers or just from kind of statements. We want to record things that help to measure the effect that their robot had on the game and anything that would help us compare that robot to the other robots. Some example things that we almost always measure are the game pieces scored, defense and their defensive skill, climbing in terms of both speed and consistency and ability to pair with other climbers, their in general driving speed, their driving skill, and then their weight/ability to be pushed around by defense.
Alrighty.
I suppose that's kind of the basic introduction to our scouting system.
Thank you. Oli, can you explain a little bit more about how we do pit scouting?
Yeah, for sure. So pretty much something that I personally have seen a lot from what other teams do, because I'm usually around in the pits and having people come up and ask questions, is a lot of people focus on that like quantitative data, like Caden was saying, on their pit scouts. They go around asking, oh, how many points can you score? How much of this can you do? But more of that data is better gotten from the stand scouts. You can get a much better grasp of it coming from that sort, because a lot of times teams have a different result in their practice rather than what they actually end up doing on the field. And usually the first round of matches where you don't really have any data isn't a big enough reason to kind of rely on that pit scout data, because it's most of the time not as accurate as your stand scout data. But the area where pit scouting really comes in through is identifying what the robots have, like Caden briefly mentioned. Identifying if they have, say, Neo motors versus Sims. Just basic stuff like that can show us what a robot can do, like in defense or just in brute like power. Sometimes, like when you get especially to your third robot or like second pick of the alliance, it's really important to make sure that you have the robot, because that's a lot of time the robot actually decides who wins the game and who loses. It's really important to decide and look through every single factor, and a lot of time pit scouting does have a role in that. Another thing that we started adopting from some other top level teams that we saw do at Worlds was to get pit scout data of the other teams, like resources. So a lot of times they'd ask about how many batteries they had or other questions along those lines. Because a lot of times once you get to finals, some of the teams that don't have as many resources their batteries tend to die, or their system kind of falls apart under pressure. So a lot of times those type of questions can come in very handy, because you know that, we need to give them a couple of our batteries maybe if we get to finals with this team. Just having those type of data points on file is very important, and those are things that you'd never be able to get just from your stand scouting.
Yeah, I'm seeing a few questions from the chat just about pit scouting in general, so I just want to address those really quick. What the point of pit scouting is for our team and how it works is that we'll have a group of people, either 2 people at a time in a pair or individuals, going around, and basically you talk to every single team, or you talk to 20 teams, another pair talks to another 20 teams until you've talked to every team in the competition. You're really just looking for qualitative data about the team, about their robot, anything that you think could be useful. We don't really do like a scoring system, so it doesn't factor in a huge amount into, for example, ranking the teams among each other when we're creating our pick list, but it does give us a lot of insight into, okay, these teams are scoring about the same, but this team is using an 8-wheel drive with more powerful motors or something, so they're going to be a little bit stronger against getting pushed around in defense, so they might be able to shoot from outside of the trench without being bothered too much, whereas a team with maybe a 6-wheel drive and weaker drive motors wouldn't be able to do that, and they'd want to sit inside the trench where they can't be touched. So we're looking for, again, qualitative data that just kind of tells you things about the robot that you might not be able to see during stand scouting. For example, during stand scouting, depending on where you're sitting it can be really hard to see the robots clearly and see things like, how does their climber work? How does their intake work? How does their, whatever mechanisms they have, how does it work? With this pit scouting, you're able to see exactly how these mechanisms work and what they do. And you can kind of judge, okay, is this mechanism going to be something that we want to rely upon heavily in a playoffs position? Or do we think, I don't know about that design. It looks like it might break or something. This might not be a team that we want to pick because I'm scared about that happening. So that's just kind of stuff that we're looking for during pit scouting. Before we move on to the next question from the chat, does anyone else want to add to that, or are we good to go?
I'll just add on real quick. Pit scouting in general is just so that way people can see essentially what the other teams are doing. Because a lot of people who are doing the scouting, like Caden said, they're also doing stand scouting, and they may not know what other strategies do teams use to accomplish the same goal. And so it gives a chance for people to go around and to see different robots and how other teams accomplish the goal. So it's an insight to give you inspiration too into that's a unique and interesting way to solve that problem. If we have that in the future, we could try doing something like that. And so since we're running low on time, we'll get to our final question. This is from Stuart from the chat. How are you communicating between all locations at the comp, between the stands, pits, and practice field? What is the most efficient way to mass communicate quickly? And I'll give this one to Ollie.
It depends on the situation, honestly. If we're asking for scouting data from the stands, we usually just bring them up and call them, because that's the most accurate way to make sure they see our notification and they actually respond. That'll result in them either coming down and talking to us or just texting over the information. If we want information to be sent to a bunch of people, say everyone, someone go over and reserve us a practice field spot at this time, or make sure all scouters keep a close eye on this match. Something along those lines. We always use Remind, as it sends it out to the whole team, and that allows everyone to be able to know. So in case, say 3 people aren't on their phones, aren't looking at it, someone else will be able to see and notify them. So it's a lot of, if you haven't used Remind, I highly recommend using it for your team. And that's kind of what we've been using the past 3 or 4 seasons, and it's helped out a lot in communication. Otherwise, just feel free to call people. Like texting is great and all, but it's just sometimes it doesn't get noticed as easily.
All right, so we're just about out of time. There's one more question from the YouTube chat. This is going to be the last one that we get to, and we're going to answer it real quickly and then transition over to our next, I believe it's a workshop that's next. Dana asked, what skills do you think are important for a scouter to have? So, Kate, why don't you give us a brief idea of your ideal scouter?
My ideal scouter, first of all, they are actually interested in what the robots are doing and how the game is played, because then they'll be more attuned to like seeing what data is actually important in terms of qualitative data, especially. They won't write something like the robot was fast. They'll write something that gives us a lot more insight into how the robot played. Another thing, I suppose, for a scouter to have would be they know how to communicate, because if they just kind of see something, write it down, even if it's something really important, they just write it down, that kind of goes to waste, at least somewhat. We want them, if they notice something actually important, then they will definitely communicate that to us right away, get us the most important information that we need.
All right, and that is going to do it for our scouting and strategy panel. Before we head out, I want to thank all of our panelists for joining us today. This was really great. I hope this was insightful for everybody watching and gives you a little more into what our team does in particular. Also, feel free to reach out to the Robot Dolphins or any of the other teams, honestly, involved with the summer series. If you have any questions about this, even teams that aren't here on this panel right now, I'm sure they'd be more than happy to help out. And that's going to do it for us. So we'll be back at 5:45 with a machining workshop brought to you by Code Orange and 5199. I wouldn't want to miss it, so please stick around. We're going to fade to black real quick, and then we'll be right back. So once again, thank you so much for joining us, and hopefully we'll see you in 5 minutes.
Oh, are we live? All right, cool. All right. Welcome to the CNC machining workshop. I'm Matthew Mosier. I'm the lead CNCer. I don't know what it's called at Code Orange, and these are my other presenters.
Hi, I'm Caden Davis. I'm going to be the lead CNCer next year for 5199.
I'm Connor. I was the lead CNCer 2019.
All right. So, next slide. All right, cool. All right. So, what is CNC machining? Some of you may not know out there. CNC stands for computer numerically controlled. Basically, what you need to know is that you have a computer with code on it that it sends off to the machine, and then the machine does whatever it does. It uses motors, and it spins its spindles, it cuts its parts. And there are a lot of different types of CNCs. The most common one for robotics would be CNC routers, and next comes like mills, CNC mills. But for robotics, the most important one would definitely be a CNC router. So any new, any team that doesn't have any CNC like machines and wants to go into CNCing would be recommended to get a CNC router, because that's the most useful for making big plates. It can also do box tubing when you set it up correctly. So you can do a lot of pocketing and whatnot to make your robots better. And like I said, there are a lot of CNCs. Like a laser cutter is a CNC machine. A water jet is a CNC machine. But it's kind of crazy because any manual machine basically has a CNC machine. There's even like CNC. There's all kinds of machines. So next slide. So why would you actually want to use CNCing? Well, CNCing is very accurate when it comes to tolerances. I think at Code Orange, the router that we have it has a tolerance of 1,000th of an inch, and our CNC mill has a tolerance of a 10,000th of an inch. So they are very accurate, and all your parts, if you set it up correctly, will come out exactly as you want them, and there's not going to be any major problems. But they're also very efficient because so later on, we're going to talk about the steps that you have to go through to create a part. And you do the first 2 steps once, and then you can recreate the part over and over by just doing the final 2 steps over and over. So they're very efficient when it comes to time and what you have to do. And also they're very efficient when it comes to like material, because you can set your parts that you're cutting right next to each other within like very, very close tolerances. So you don't actually have to waste a lot of material that you're cutting out of to make your parts. And obviously, they're probably faster than a normal person just trying to do it on like a manual mill or some other manual machine, because it's a robot doing it, basically. And you can set all your feeds and speeds correctly, and it will be running through your parts at high speed. Next slide.
To add on to that really quick, another important factor when considering the accuracy is the repeatability, because you are just repeating a set of machine code instructions. So you are able to make identical parts. Not only are they accurate, but you can make 40, washers that are all the exact same diameter within an extremely tight tolerance.
Oh, that's a good thing go back just real quick. There's one important thing that I wanted to say that I ran into because I run our CNCs, was that you also have to make sure that what you're cutting out of, the parts, like the part blank and the stock that you're cutting out of, is within your tolerance as well, because we actually ran into a problem where we were like, why are our cuts off? But it's actually because the tubing that we had was way out of our tolerances. We just never read our tolerances. So if you're going to be CNCing, make sure that the stock you get is within your tolerances as well. That's just an important point note. So, and technically 3D printing is a type of CNCing, but it's often like something that kind of competes with it. But they're very different in a lot of ways. So CNCing, obviously, you have usually a big just piece of metal or whatever you're cutting out of, and then you cut away to make whatever part. Well, 3D printing, you add to it, you're putting plastic down to make whatever part you're making. And like it says here, that it's typically a little bit more expensive because you're actually using metals instead of just using basic plastics, because it's very difficult and also expensive to get the 3D printers that use anything but plastic. So it's often better if you're making metal things, obviously, to use CNCs. And you can also use polycarb and whatnot on a CNC. And the major problem with CNCs is that it's very difficult to make very complex 3D things when you're cutting instead of just additive machining like it says here. So it's better for 3D printing if you're trying to make very complex things. And there are larger tolerances on 3D printing instead of CNCing because of like thickness of your plastic and whatnot. And it's important to like think of all the aspects of whatever you're making before you choose what you're actually going to be using. Yeah.
So the CNC workflow comes in 4 basic steps. First, you have to decide what parts are you going to be making using the CNC. And that comes from the CAD, which, as you guys most likely know, is computer-aided design. That's where you design all the parts for your robot. Then you switch to CAM. This is a product like SolidWorks CAM or Autodesk Fusion. This is computer-aided manufacturing. In CAM, you take the parts from your CAD and convert them into the instructions that the CNC, will run to make the part. Then you have your CNC setup, which is loading the material properly, making sure everything is correctly calibrated, making sure you have the right size cutting bit, the mill tool for the CNC. And finally, you have the CNC machining, which is where the machine actually executes all the instructions you have given it. And hopefully you produce a nice batch of parts.
I have one caveat to the computer-aided manufacturing CAM. A really good CAM software that actually can just be added on to SolidWorks is HSM Works. We use it at Code Orange, and we've had basically no problems. There's some really good stuff you can do in that. So that's another CAM software you're able to use. And
to add to that, even at 5199, we use Autodesk Fusion 360 because we're used to it. We know it. We find it works for us. Yeah. So really everything, there's a lot of different great programs out there that are usually free. So this kind of expands on something we talked about earlier, the ease of machining different parts. So the parts you see on the left here are like the perfect parts for a typical CNC router. So a standard CNC router that would be accessible to robotics teams without hundreds of thousands of dollars are called 3-axis routers. They move X, Y, and Z, and that's it. So they are really good at making simple geometries, very good at parts that have 2 flat surfaces. So just basically flat parts for the most part. The 2 examples on the right, those are parts that would be like impossible basically impossible to produce with a standard 3-axis router. So the middle example, this is a complex pipe. So the reason that this would be impossible to make is because you wouldn't be able to carve out that bend in the material because your CNC machine can't kind of snake its way down. It can only access like certain surfaces. It can't access inside surfaces. And then the part on the right here, that lip that you see overhanging that would prevent a standard 3-axis mill from reaching that inner surface. You notice though that the machine there is able to cut it. That is known as a 5-axis mill. That is a kind that you can rotate the head of it to access more difficult to reach surfaces. But in general, that would be inaccessible for FRC. So here are we're going to introduce some vocabulary related to CNC and machining. So the tool path is the name for the instructions that the CNC machine is going to execute. So you see on this path or on this cam here, that green path is the outline that the spindle, which is basically the spinning cutting bit, is going to follow as it cuts the material away. So it'll trace that line again, all the way down until the desired thickness is cut. Then our next term is the 0 point, also called the origin. It's just like it is in math. It's 0.000, where just x is 0, y is 0, z is 0. This changes depending on your team's preference. Like I know for our team, we put this in the front left of the sheet. Other teams might choose the back left, for example. It really is preference. You just have to make sure that you correctly calibrate your machine depending on what you set in CAM. Here are some of the common toolpaths we used. So 2D adaptive clearing is also very similar to that one at the bottom, 2D pocket. This is what you would use if you are trying to clear away a surface of material. For example, if you're trying to carve a 1-inch hole in a plate, a 2D pocket would go back and forth across that hole, shaving away the top layer, go over it again, shave away that second layer, and repeat that until you have carved out that hole. 2D contour is a bit different. In this, it traces an edge. It doesn't cut away an entire area. It only cuts around the edge. So an example of this would be just the outline of a part. Like let's say you're making a plate. This would be the outline of the plate because you would just trace along that edge to separate the plate from the stock, which is the material sheet. Our final one is bore. This is used for smaller holes. Think 3/16 or 1/8. In this, because you're carving away so little material, then the router's bit is able to just very quickly plunge into the material and just cut away that tiny amount. You would use a bore if the size of the hole you're cutting is pretty close to the size of your bit. And you would use a 2D pocket if the hole is a lot larger than your bit. So this is a CAD consideration to make when you are camming parts. Sharp inside corners are really difficult to machine because if you think about it, you are using a spinning bit that is basically a cylinder. So it's not able to produce that sharp corner without cutting into it more, as you see on the right. Just because if you go all the way up to that corner, then you have a round bit and that would leave a slight rounding on it.
I have one
caveat.
That if you're making something like this, you see here where it's a like a spacer or something. For something like this, what we do at a Code Orange is we actually cut a circular hole that's 1/2 inch. I think that's 1/2 inch.
Yep.
And then we use it's called a hex broach. It's a very useful thing that most teams should have if they're making stuff like anything that's that uses 1/2 inch hex rod, and it basically turns a circular 1/2 inch hole into a 1/2 inch hole for hexes. So that's a useful thing that we use at Robotics.
To add on to that a tiny bit, if I recall, correct me on this, you need with the hex broach some kind of press, whether an arbor press or a hydraulic press, to punch the hole. Yeah. So when you lay out parts in CAM, you first of all want to make sure that your axes are correct. This is done by making sure your 0 point is in the right place and that your X direction, Y direction, and Z direction are all running in the directions that you want. For example, positive Z we set as the upward direction, and we just have to make sure we account for that in our CAM layout. When you are laying out all your parts, what you most want to do is maximize your efficiency and your yield, because it takes a lot of time to set up the CNC with putting on the material sheet, securing it, making sure it's calibrated, that you want to get as many parts as you can from a single setup of the CNC at a time. you also want to make sure you get as many parts as possible with as little material wasted as possible from your sheet of material. So as you can see in this example here on the right, we pack together most of the parts really tightly as we can, making sure that we don't set it so tightly that the bit will cut into the other part as it passes through. But we want to make sure there are no big blank regions where we could have fit another part and gotten more use out of the machine and out of that sheet. That just ends up going to waste because it really is just wasted money.
Oh, could you go back a slide? I just want to interject on the end of that. You also want to, when you're laying out parts, make sure that you don't make islands. You don't want to have an island of material that gets cut loose because that'll just kind of jump around in your bed. And that can end up breaking bit or whatever, jumping out and hitting something.
So some more vocab words. We kind of introduced this earlier, but the stock is the actual sheet of material. In this case, that picture is of aluminum stock. The setup, we kind of say the CNC setup is the folder containing the G code, which is the set of instructions that the CNC machine runs. So in that little diagram there, on the computer, you produce the setup, and then using a flash drive or some other kind of file transfer, however you do it, you transfer that folder and the contents to the CNC machine where it executes those. So in your CAM settings, there are a lot of different settings to play with, but here are some of the most important ones. Your top and bottom offset. This tells the CNC's bit how far should it go down when it is cutting through the material, and how far above the surface of material should it go when it's moving. These are very important to set because so first with the top offset, if you don't set your top offset correctly, then your bit might not fully retract from a deep hole and end up breaking itself as you try to move out of that hole when you aren't fully out of it yet. For the bottom offset, you want to fully cut the material free from the sheet so that it's not connected by a thin layer of metal, because that leads to just burrs and makes it more difficult. But you don't want to go too far down because that'll cut into the board underneath the stock and damage that. The depth of cut kind of ties to that. That's how far should we plunge down to make sure we fully get through the material. And when managing all these different settings, I know at least for Autodesk Fusion, and I would presume for SolidWorks HSM Works, you can set defaults for everything. We have a default setup for 3/16 aluminum, a default setup for 1/8 aluminum, and so on, to make sure that all our settings are accurate and kind of standard.
And if I can hop in on this one real quick as well.
Yeah.
A couple of times that you kind of see that you want to use these is we use our top offset because sometimes our material is kind of bent up in the middle, kind of bubbles up just from how it's set down. The bottom offset, sometimes our zero is a little bit higher and lower in different areas. The MDF bubbles up in a couple of spots. And
the MDF is the board underneath the stock, by the way.
Spoil board.
Yeah.
Could you run back just one more? And the depth of cut, that doesn't apply to everything. For us, it's just we have to use it because our end mill is a single flute. It's on a kind of low torque motor because it's mostly a wood cutting router, ours, and it's just modified. And we can't clear out a ton of material at once, just like you can with a full-size mill like Code Orange might.
Yeah, we have to kind of do multiple runs on a hole. Like we poke at it, get a bit deeper, come out, remove the chips, go again, cut the hole a bit deeper and repeat until we hit the desired depth.
We do the same thing on our router, and on the CNC mill that we have. We just go all the way to the bottom, and we don't need a depth of cut. We just go straight through on the mill. But on the router, you definitely need a depth of cut because usually your bit is not good enough to just go straight through it. So
yeah, your bit will typically snap. So
you'll jam up and it'll just break because the motors will keep going.
Mm-hmm.
All right.
So cam simulation. Once you've configured all your settings, made your toolpath, told it what to cut, you can simulate your cut where it'll draw a fake spindle, as you can see at the bottom there, and just kind of in cam run the cut on a sample stock and show you what your cut's going to turn out like. This is very important to do before you commit the time, the resources, the money, because it lets you just ensure that your cut is smooth, functioning as intended, everything is calibrated, and that you haven't missed any lines or selected the wrong operation for another line, for example. Yeah, just to make sure everything is smooth.
And this is also a really good spot to check for those little floating islands of material that can pop out. Because if you check to show stock and don't show the toolpath, you can actually see it like it would be once it's done cutting, like how your board would look at the very end. And you can see if there are any random floating parts that don't have a tab or whatever, or unsupported ends that you might need to worry about. And you can just go back and move things around to make it work right.
So post-processing is kind of the transition from CAM to CNC setup. In this, you have to configure a whole bunch of settings for your machine about, so for example here, NC extension .nc, that makes sure our code is compatible with our router. Really, all of these settings are just to go from the language of CAM, which is diagrams and CAD-like surfaces, to a toolpath and just generic instructions like move Y to, for example, on the actual router. So it's basically translating from CAM language, which a human reads, to CNC language, which the CNC reads. So in the normal operation of a CNC router, you need three supplies kind of commonly. You need end mills, which are the bits that actually do the cutting. There are a range of different sizes and a range of different flutes. A flute is kind of that groove you see where the bits, or where the little chips of metal get carried out. You need coolant. This is very necessary if you are cutting metals like aluminum, because they will produce sparks and other things that you don't want if you don't keep everything cool. Also, the coolant helps to keep the chips from flying everywhere.
At Code Orange, Code Orange, we don't actually use a liquid coolant for our router. We air cool our router, which makes it so we have to cut a little bit slower, but it also works. So air cooling a router is a possibility. We've been doing it for years, but if there's some problems if you use liquid coolants for us, but usually it's air coolant for just putting a ton of compressed air over our parts.
Yeah, a couple of things with the liquid coolant. The big thing is it just lubricates. It's like a cutting oil sort of thing. And but one of the biggest problems is if you use a MDF spoil board, it'll just get in there and the spoil board starts to kind of bubble up just because it's made of wood. It'll expand when it gets wet.
Yeah, that
starts to throw off your tolerances.
That picture is using a lot more coolant than what we would use in operation. We don't want a big layer forming of coolant on the surface of the material. We want just enough to keep things lubricated and cool without ruining our MDF or wasting coolant.
Yeah, with ours we just... Go ahead.
I'm gonna get into the next topic, so if you want to finish.
Oh, I was just going to say the pictures of flood coolant. That's really good for mills and things where it's all in like one little unit. You don't have to worry about a spoil board. It's just on your material, and we just use a light mist, very very light, of coolant.
The final thing that you need, hopefully this seems obvious, is the actual material sheets that you're going to cut from. So it depends on the team and on preference of how many material sheets you want to keep on hand and of what. I know at 5199 we like to keep a couple sheets, usually 2, 3, 2.5 around there, of 1/16 and 1/8 6061 aluminum, just because in a given night we could easily go through 2 sheets of that, and we don't want to be caught waiting on the metal suppliers when we're trying to make progress on a robot.
At Code Orange, we have a, I don't know, it's just a place we store all our metal and wood and polycarb, and we store a lot more of metal and polycarb. If I just think about it now, we probably had 20 or more sheets of metal there, but they're all different sizes and all of different shapes and whatnot, and a lot of it's been used. So a lot of it for us is we just have a lot of material sheets at Code Orange.
Yeah, we have a cabinet with 15, probably 15 half-used sheets. If we're making just a couple parts, we'll throw those on, make sure we get our money's worth of the sheet.
All right, continue.
Yeah. Setting up a CNC router. So this kind of ties back to what we said before. You first load the material sheet onto the CNC board. In our case, it's the MDF spoil board. So when you load the material sheet, you want to make sure it's secure, because if you try to drill into something or mill into something that's insecure, then it will go flying everywhere, it will shake around, and it will likely break your bit just because the metal moving around is going to bend it. So we do this in 2 ways. On the back of the sheet, we apply a special double-sided tape to help the sheet stick down to the MDF board, but also along the edge of the sheet, we screw it down using, I thought I had a picture on here, using just cap screws. You don't want to use a button head. You want to use something with as much surface area to hold down as much of the sheet as possible. Then you will zero the spindle. You do this using a little remote control. You move the spindle to whatever spot you want to set at 0, 0, 0. And then you click the set button and it's calibrated. Finally, you will set up whatever coolant method you have, whether it is air coolant. I know for us, we use the mist coolant. So we will turn on the pneumatic valve and turn on our coolant valve, wait for it to start spraying, and then we'll start our cut.
And real quick on the last one, some of them will you don't open the valve yourself. It's controlled by the machine, like some of the higher end mills and things.
Yeah.
They'll automatically just open and close their coolant. So it kind of varies machine to machine, yeah.
And here are some resources if you guys want to mark those down really quick. I'm gonna actually, oh, never mind. Here, I'll go back to presenting. Hold on, sorry. All right, there you go. If you guys just want to mark those down really quick, these are 3 sites I've found that are really helpful for introducing the concepts of CNC and a lot of the terminology you might find. If you guys want to present any questions you guys have in chat, we're open to answer them.
I've seen a couple pop up. One that I want to answer real quick because it was just at the end on the coolant topic is the difference between liquid and mist coolant. it's more of the difference between flood coolant and mist coolant. They're both liquid, but mist coolant is more of a spray bottle sort of thing. You're just giving it a little, like, fine layer of a coolant. Flood coolant, you're just shooting like a whole jet, like out of a hose. You're just in a ton of coolant, so everything's cool. Everything's covered.
Flood coolant is like pressurized liquid just shooting out, while mist coolant is introducing a little bit of liquid into a stream of pressurized air to kind of vaporize it and disperse it. I'm not able to see the questions, so if you guys could share what you guys are seeing here.
I'll bring up a couple more.
Great.
Yeah. One that I just see is where do we typically purchase tools like end mills, and where do we find our feeds and speeds? Do you just want me to go at it with that one?
Go ahead.
I do the feeds and speeds thing.
Sure.
The end mills, you can get them off of like MasterCar. You can get them. There are a lot of places to get them, really. I think ours are all off of McMaster. We use Onsrud, I think, is the company that makes them. But carbide, it's a kind of a joke, kind of truth. The Chinese carbide works really well. So you can get carbide, but really cheap from kind of anywhere. And feeds and speeds. Oh, do you want to go ahead?
Oh, yeah, you can go ahead. Yeah.
Okay. And on the feed speeds, that kind of varies depending on your machine's capabilities and your end mill's capabilities and your coolant and a lot of factors. I usually just start it low. With our router, the speed control isn't the best on the motor. And so I just spin it up to max speed and start at a low cut speed and gradually increase it until it starts being kind of unhappy noises. It's kind of just a thing that you get a feel for generally over time, gradually.
Yeah.
There are calculators, though, for higher end mills and end mills.
So one of the important things that you have to understand is that most materials have a surface feet per minute, I think, that is good for them when it comes to cutting. So you often want to search up what the surface feet per minute of your bit should be when it comes to cutting. And then there's a lot of, like they said, was online materials and online calculators where you just put the surface feet per minute, the size of the bit, and so on, and it'll come out with what speed you should run it at the feed rate is definitely has to do with how well you cool it, but the speed you should run it at comes from the surface feet per minute and the size of the bit.
Definitely. So hopefully that question is sufficiently answered. Connor, if you could share us
Oh yeah, I'll keep going with the questions. CAM software, that was already kind of answered. Fusion 360, HSM works, SolidWorks CAM. Master CAM is another popular one. That's a little bit higher end.
There's like an auto cam that we got access to. We haven't really used it, but it has some crazy capabilities, I think. So I don't remember what it's exactly called, but it's kind of insane. There's a lot of things you can choose, but for most of our work, we just do HSM Works.
Yeah, and a lot of that
HSM Works. I think that's for you with SolidWorks, isn't it? Or at least the education package. Yeah,
it is.
Yeah, a lot of the different software for CAM, CAD, whatever, you can find by looking up FRC free included software, because a lot of companies give you free software when you are an FRC team. Any further questions?
Yeah, I'm going through them right now.
Great.
Oh, it dropped all the way down. Hold on. Okay. So for a hole inside of a part, should the CNC make a contour or a pocket? It kind of depends on the hole. You can kind of get away with, if you're making a really teeny tiny hole that's less than twice the size of the end mill, just doing a contour. But if it's any bigger than the end mill and it'll leave anything on the middle, you want to do a full clear. Or you can in the past, we have done a contour and given it tabs on the edges that we just cut out afterwards.
So the way we do it at Code Orange, it's kind of, I mean, you could consider it kind of sketchy, but if we find the center of the, like, if it's kind of a decently sized hole and we really need to finish the part fast, we will make it a contour. I don't really think this is a good idea to do, but we do it anyway. We just drill a hole through it like a hand drill and then screw it down as well, like with just a screw. And that works. We do it with some of our parts, but it's probably not the best idea.
Yeah,
we definitely do that sometimes when we're in a rush. As Connor
It's
said-
especially oh, sorry.
No, go ahead.
Okay. We do that especially if there's a huge cutout that we need to make. Like, I think at one point I was cutting out a bracket to hold a battery in. That one, I just right away, I made some little holes in the middle section that was going to be cut out and put screws in them, because to clear out that whole thing, it would have taken like days.
Yeah.
With our little end mill.
What we tend to prefer doing, as Connor said, is tabs. And to get into that a little more, tabs are really thin little bridges of material that the CNC doesn't cut out. It'll actually just kind of hop over it as it cuts to leave that little really thin layer of metal or plastic, if you're doing polycarb, that you can usually snip with a pair of dikes and still have a relatively smooth surface. We prefer using those in most cases just because they are secure and they don't require additional setup, which on the human end, which is a lot easier to mess up because we have put the screws wrong before and milled into the screws, for example, and other things like that.
I have one last thing to say is that the real specific time that pocketing is like required for us is when it's a bearing hole, because it's we found it to be more consistent when it comes to size. If it's a bearing, if you pocket the bearing hole, no matter what, you never contour a bearing hole when it comes to when we're making parts.
One other use of pocketing that we have is on the drive tubes. Along the sides, we pocket out patterns in them of usually triangles, partially. So let's say it's an 1/8 inch thick. We will pocket out 1/16 of that just to save weight without compromising the strength too much. So just thinning out the material without fully cutting through it is another use of pocketing.
Any other questions?
Yeah. Let me grab the next one. Do you set your work offsets with a probe or manually? I think that probably varies between our machines and our teams. So if you guys want to talk about that some.
Yeah. All right. So at Code Orange, we set on the router, we set the 0 point, the XY of the 0 manually, but then we have a distance probe that we just put on the CNC router part, and the bit will just like go down towards it slowly until it touches, and it knows the height of the probe, and it'll basically put the 0 of the Z on the face of the part. And on the CNC mill, if you have a CNC mill, it probably has like an automatic probe. If you like you usually buy an automatic probe with a CNC mill, and those like do everything automatically basically. So
here at 5199, we don't have that Z-axis probe, so we just slowly lower down the bit up until it is touching we slowly spin the bit and bring it down to the face of the material up until we feel significant resistance. And then we go, I believe it's 1/10 of a millimeter up from that. It's definitely not the most accurate, but we are able to make up for it using larger top and bottom offsets, which we brought up earlier, just in case we're off by, say, 0.03 millimeters or something very small like that in the Z direction. So it's definitely not as accurate as a distance probe, but we found it gets the job done for us, especially when cutting flat parts.
All right, do you guys want to go to the next question?
yeah.
All right, so
Okay, yeah.
This is-
I think this is the last question, though.
no, there are a couple more heading up.
No,
I've got them written out here.
Time-wise.
Oh yeah, we're running out of time.
So just cut us off
Um,
whenever. Cut us off when we're running out of time. But let's go. Next question.
Yeah.
Right, this one's a good one. That's pretty topical. Does the CAM software have a way of putting the tabs onto the piece, or is that done in CAD? Do you know how
it's done
to
in-
slide 9 real quick, Caden?
Oh, yeah. Oh, what? Sorry?
Can you go to slide 9?
Oh,
The one
sorry,
with the two green things.
There
That
we go.
one. So those are tabs, the little blue spots bridging between the green spots on the two right images. And those were all added in CAM. Those were, we use Fusion 360. It lets you manually place them in a contour or just have it automatically some X millimeters.
All right. Last question. We have 3 minutes to our next presentation.
We've got a little bit extra time. I was just told that we have a little bit extra time.
Oh, okay, great.
What are the recommended sizes for a new machine? That's a good one.
Oh.
I want to hit real quick.
I think our machine, our router, is it supports. I think our bed is 5 by 5 feet. So we usually use 4 by 4 plates, 4 feet by 4 feet plates as our like stock plate, and it goes up a certain amount. But yeah, you want it so that whatever, like we use 4 by 4 plates, so we definitely need it a little bit bigger on our router. So if you're going to be using big metal sheets like we do, then you definitely need a very large router.
We use a bit smaller sheet. Basically that cut in half. It's been a while, but I believe it's 16 by 31 is
That
our
sounds right.
approximate cutting surface. So if we get a sheet that's too large for us to use on the router, we'll cut it down with, say, a saw, just so that it does fit on our machine.
And they also said bit sizes. We just use a 1/8 inch end mill and a 3/16 inch. The 1/8 inch we exclusively use for bore operations to cut our holes, because most of our holes are 3/16 inch, and we don't like to peck drill. And the 3/16 inch we use for all of our pockets and contours, because it's a lot stronger, just with the extra width than the 1/8 inch.
At Code Orange, our main bit, kind of surprisingly, we always talk in the like American units, the whatever they're called, but our main bit is actually a 4 millimeter bit, and it's a 1 flute. So maybe we should talk about flutes a little bit because they're kind of important. But basically, the basic idea behind flutes is that a lot of flutes is really good at like it has a better surface finish than 1 flute, and there's other advantages, but I know that a 1 flute is very good at clearing a lot of material. So we use a 1 flute 4 millimeter for most of our stuff. Anything smaller, we'll just use a smaller bit like an 1/8 inch or whatever. And for bigger stuff, we'll probably we don't really we just use the small bit and then just contour around it. So, any other questions?
That was the last one that I had time for. I'm just going to type a couple up in chat. There are questions that I can just answer real quick.
Great.
Those are kind of the big ones that I think were good discussion ones.
I'll start to wrap us up here. So we are going to have another presentation in just a minute. There's been a slight delay. It was going to be at 6:30. Now expect in the next minute or two. Join us or join team 3309, the Fryer bots, as they discuss fasteners and their role in FRC.
Right.
I'd like to thank our presenters here. Thank you guys for coming to watch us, and we hope you enjoyed.
Mm-hmm.
Oh, hello. Hi, I'm Tyson Lee. I'm a mechanical engineer mentor at 3309. I just want to thank Dolphins at 5199 and for dry and basic, but it's really necessary to put these robots together. So we're just going to talk about fasteners and holes by screw sizes and drill bits and taps, nuts, and rivets all included. So first thing is going to be about machine screw sizes and then the different screw heads. And you can't really talk about fasteners without holes. And that's why it's all about fasteners. We'll go into how to drill a hole and some tips on how to drill a hole and how to tap the hole and why or why not you may want to use a nut. And then lastly, rivets. Not my favorite fastener, but a lot of teams like it. So what is a machine screw? On the right here, you'll see a bunch of typical machine screws, and they're different from a wood screw. And then terms like bolt screws, fasteners, they're pretty much used interchangeably. It doesn't really matter what you use. They need to be fastened into nuts or threaded holes to be used, but really, it's most important. They're not usable without. They have to be matched to the screw or the nut. And there's inch and metric standards, and they're defined by thread geometry. And this little lower diagram here, don't worry about it if you can't read it. It's the reason I put it in there is very specific as to what screw size is, and it's very important to how it is made. So there's going to talk about the standard inch sizes. It's always going to be expressed in threads per inch. And so if you take a 1 whole inch and take a caliper and put it across a whole inch, you just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 threads per inch. So then that would be the first thing actually is you're going to measure it by the major diameter here. And if this is
Tyson,
a 3/4 10
a little bit. I don't think we missed a whole lot of information, but just be aware that you are cutting out every, I'd say a little bit once every minute for a couple seconds. I guess we'll just have to go with it, but I'll let you know if there's any big cuts. But right now it's just been a couple seconds, and I think it's been okay.
All right. Yeah, I am, and I know I am talking a little fast, so I'll try to calm down and slow down a little.
Okay, sounds good. Carry on.
Okay, so I don't want to go too far into it, but there are metric threads, and they're a little bit different. They're very different than the inch threads. The threads are defined by the pitch between the distance between the threads. It's very, it's different than how we do threads per inch. But don't worry about it. 95% of the screws you'll ever use here around here is going to be inch, but there are definitely metric screws out there. So watch out, and if you don't have a trained eye, you're not looking out for them, it'll work. So machine screw sizes. There's a chart you'll see in every shop. And you'll see machine screw size up here, and there's numbers. You express the size of the screw by the number, going from 0 to 12 here, and then it goes into fractionals. So there's far more fractionals and sixteenths, maybe a 5/16.
Could you
what I really
last bit, Tyson, you cut out for an extended period of time when you were just talking about number 12?
Talking about number 12 here?
Yeah.
Yeah, okay. So what?
Oh, you're cutting out again.
But I guess, wow.
You're back in now.
Let me see. Let me pull up. Oh wow. Okay, so let me see if it's this mic or something.
For the stream, we're going to cut some audio for a second while we finish doing some mic testing. We'll be back in a couple minutes.
All right. Seconds. All right, one. Okay, so I'm back here. Hopefully this is gonna continue on. We'll just have to power through this. So what I wanted to point out is that there's different sizes of screws here, and then even in each one of these screws, there's two different sizes. So you can have a 1024 or a 1032, and that's going to be covered by the Unified National Standard.
You did cut out for about 2 seconds there.
Wow. Okay, so I don't know what I can do. I think we're just going to have to power through this, right, Kyle? All right. All right. Yeah, so by far we're gonna find on FRC size robots, you're gonna use a 1032, and a 10 is actually so a 10 right here is defined by the major diameter, and that's what we talked about earlier. That's what I showed you around earlier, where so you can have the same major diameter and two different thread pitches, but really you never want to use a 1024 around here. You don't. They're really, because they're the same size, you're bound to mix them up, and they just don't go into each other. So you'll also see a lot of quarter 20s, 832s and 632s, less common. 440, you'll see definitely for sure on electrical boards. There's a whole lot of other sizes,
okay, so
but
you did cut
this is a theme I'm gonna.
but there is a suggestion from the stream chat. They said you could try joining Google Meet on your phone and doing the audio from there and muting your computer and just control.
Sure.
There. Do you want to try that?
Yeah.
Okay. We'll be back in a couple minutes. We're going to cut audio again real quickly while we come back. Thank you for waiting with us, stream. And we apologize for the technical difficulties.
Hi, welcome everyone. This topic is on fasteners and holes. My name is Tyson Lee. I'm a mechanical engineer and a mentor at 3309. I just want to thank 5109 Robot Dolphins for inviting me to give a talk on this subject. We're going to go over machine screw sizes, different screw heads, holes and drills, and how you make those holes using a drill, and how you might tap that hole, and why or why not you may want to use a nut and rivets. Not my personal favorite, but it's got to be covered. So what is a machine screw? On the right-hand side here, you see a bunch of these screws. They're called nuts, bolts, fasteners, whatever you want to call it. They're a little bit different than a wood screw in the sense that the wood screw is meant to be self-tapping into, obviously, wood. And these fasteners are really meant to be fastened into nuts or threaded holes. They really have to be matched to each other, the screw to the nut. There's inch and metric standards, and they're defined by this type of thread chart here, or this thread geometry. Don't worry about seeing it or reading it too much, but just know that it's a very specific geometry that it's defined by. There's standard inch and metric screws. The way that they're described is very different as well. The inch threads are threads per inch. So if I were to take an inch distance here and count the threads, it would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that would be 10 threads per inch right there. On a metric size, you'd actually describe it by the distance between a thread, and then you start off with the major diameter by measuring the diameter of the screw, the outside of the screw thread, and that's the major diameter. So if this was 3/4 of an inch and 10 threads per inch, that's a 3/4 10. On a metric, it'd be an M25 by 2.5. A little bit very different than how you would express it on an inch thread. But don't worry, 95% of the screws you'll ever use here are inch. But good to know that the metrics exist, so watch out for those. So in every shop you're going to see a tap chart or a hole chart here, and we'll just start on the machine screw sizes on the left side here. The numbers are going to go from 0 to 10 or 0 to 12, and by the major diameter, it's going to go by size. So it doesn't really correspond to anything, exactly to the decimal size. It's just a standardized diameter. And then after 12, it goes to 1/4 inch. And then, of course, there's larger than 1/4 inches. But generally, you're not going to see anything larger than a 1/4 inch or 1/4 20 or maybe 1/4 28 thread in FRC. For each thread, there's also a thread size. There's also a coarse thread pitch and a fine thread pitch. And you'd express that as 1024 or 1032. By far, there's 1032s are used on FRC size robots. It's just a good sturdy size to use. Sometimes you might want to use a 1/4 20, and then go down to an 832 or a 632. And there's only like one instance that I can think of that you'd have to use a 1024, but you don't want to keep those two together. It's a recipe for disaster. And then just know that 440s, they're pretty small, but they're very commonly used for electrical boards. Lots of other sizes exist. The whole point here is to limit the screw sizes available to you, or there's lots of screw sizes available to you, but you want to limit the screw sizes that you actually use to help standardize your screws. And it's going to be a common theme moving forward here. So screw head types, lots of different screw head types. There's no other reason, there's no other way for me to explain it, why there's so many different screws. You're going to see architectural, automotive, carpentry, and there's just no other reason other than various uses in history. So we're going to use a hex socket, so 6-point, because the actual hex driver that you use provides really good torque and a non-slip torque. And because we've standardized these screw sizes, we only need several hex driver sizes. So if you only use 1032s and quarter 20s, then actually it becomes really simple that you only need to use a 1/8 driver or a 5/32 driver, and that would be a blue and a red. And makes it really simple to work around the pits and kind of you really get to know the screws, and hey, I need a blue, hey, I need a red. That's really going to be simple to use in the pits and putting the robot together. Phillips head are still used, these 4 points here, and flat heads like this, but really try to use a hex head because it's just a lot more firmer. I'll talk about flat and countersink screws a little bit later. So when you specify a screw size, you talk about the thread pitch, and then you have to talk about the length. So the length is the length of the screw right here from underneath the head to the length of the threads. What's a little bit different about a flat or countersink screw is that you actually measure it from the material, the top of the head, to the end of the screw. So really what's inside the material is what the length of the screw is. So you'd express it like a quarter 30 or 1032 by 3/4 inch, or 0.75, or quarter 20 by 1 inch. And the other thing that I want to point out about when you need to use a countersink, you have a minimum plate thickness that you have to be using. That plate thickness has to be the head of the thickness of the head. If you use a cap screw, then you don't need to worry about that. You can use as thin as you want or as thick as you need to. And then just another warning: please don't force a screw into a nut or a thread. If it feels tight, check to see if the thread is correct. Something's cross-threaded or in the threads blocking the holes. The screws can break very easily and cause just a big problem later. I'm going to gloss through this slide really quick. There's a lot of good engineering in here, but I think it's just a little bit out of the scope of this discussion. What I want to show is that what I really want to stress here is that you don't want to torque it too much, and you don't want to torque it too little, or else it'll just fall out. So how much you really torque it to? Just give it a feel. It's very much a feel between a 1/8 to a quarter inch turn, past finger tight. I've always called it German torque. It's good and tight, and you kind of get a feel for it as you keep going. This is another funny slide to me. These are all the type of specialty screws that you can think of, but really none of these are real. These are all just a bit of a joke. This offset bolt for mismatched holes. When you think about it, a screw just isn't going to work when you look at this screw, or even this one looks just really funny because the hole is too near the edge, right? I mean, these are all the problems that you could come up with when you deal with the holes and fasteners. Even though the fastener looks so simple, there's lots of reasons why, lots of ways for it to go wrong. So like I said, you can't talk about fasteners without talking about holes. Every fastener goes into a hole. Holes are made with drill bits. You've all seen these drill bits before. You put them in a hand drill, a drill press, a lathe, or a mill. Drill bits are tightened in the chuck or a collet on a mill. It's nice to have a full set. I'll admit that it's really nice to have every little fine drill size available, but you don't need all of them. If you want to know what the drill size is, it's always marked on the end. If you can't read what's on the end, then you just use a caliper. The size of this shank is always going to be the size of the size of the drill bit, unless it's obviously not. So all those drill bits, there are charts to show everything about every size of a drill bit, and there's lots of them. There are standard drill sizes of numbers, letters, and fractions, but what really matters is the decimal equivalent. So smaller the drill, the larger the number. So there's really tiny drills, and there's even tinier drills in this side for sure. But then when you get up to about a 1/4 inch, it goes to 1. And then it jumps up to letters. And then it goes to letters, it'll go to fractions. It'll just simply go to fractions. So why are there numbers? Why does it start with numbers? It's just because at really fine divisions, it doesn't make sense to do anything other than, it doesn't make sense to have fractions. You couldn't really have these fine divisions of an 039 and an 040. Then you throw in metric drill bits. Then you have all these drill sizes to think about. But good news, we only really need to drill to have holes for a very few sizes. So back to this chart, you're gonna drill. You're gonna, for every screw fastener, you're gonna you need to create a clearance hole. Now, this is why you have clearance. You need to have the hole size larger than the major diameter of the screw, and that's always going to be, the hole can't be smaller than the screw, and of course there's different ways there's different standards. Either you want to have a close fit or a free fit or a normal fit. I mean, you go into SolidWorks and you'll say, I want a precise fit. I'm going to say, I mean, this is my big point here, that a tighter fitting hole does not mean you'll get a more precise fits, because you need those clearance to fit the parts, and not everything is or can be made precise. The tighter the hole, if you tighten the hole too much, then the parts aren't going to fit. Then you go ahead and you try to assemble your robot, and you're going to end up drilling the hole out anyway, and then you lose your precision that you put into the locating that hole. So obviously, a grossly oversized hole isn't desirable either. So out of this chart, I would recommend a free fit here, and there's going to be a good reason later too. So for the 1032, you don't want to use the number 7 201 size. To drill a clearance hole. And again, because we standardize these screw sizes, we only need to have these 3 screw sizes, three drill bit sizes. A little more into the drill anatomy. I want to point out that a drill bit isn't pointy sharp. If you actually take a really large drill bit, you'll look at the end of it, and it's got this what's called the chisel edge, and it's very well defined as to how it creates the cutting edge to the edge here. This cutting edge is really where all the work gets done. It's because theoretically at 0 here, it's got 0 speed, so it's not going to do any cutting. So they put that chisel edge in there so that you get it to a point where it can actually start to do the cut. Now, that chisel edge is actually what makes the drill bit walk away from you when you try to do the first drill. So I'll talk about, so you always want to do a pilot hole or a center punch to get underneath this chisel edge here. So how to drill a hole? Scribe a line or a crosshair where you need to. Because this is an online, I can't. Normally, I would show this would be much more of a hands-on demonstration, but scribe a line, center punch or center drill using a mill or lathe, and pilot drill a smaller hole. I recommend an 1/8 or 3/32. You should have plenty of these available. They're really cheap. They're plentiful, and you consume them really quick. And then you can just go ahead and go to the final drill size. when you use a drill press, it keeps it nice and vertical and rigid. But most often, a lot of times, you're going to be drilling by hand. Some things to keep in mind is to keep that drill bit perpendicular to the surface. Don't bend the drill bit. So drill bits don't like to be bent. They don't like to be going sideways. They're not strong. They're not strong radially. Every time you bend a bit while you're drilling, you're essentially flexing it like a plastic spoon, and that little thin drill bit is not going to last. And then don't clog the flutes with material. Frequently back it out, blow off the material, and it'll definitely cut a lot better. And of course, it'll cut a lot better with when it's lubricated with metal. If you think it's not cutting, and just throw it away, because you always want to wear safety glasses when drilling. Bits break so easily, and when they break, they go flying, and that very possibly it can go flying right into your eye. Just throw away the broken bits. If you break a bit, just throw it away. Don't try to put it back. Please don't try to put it back and think that you're ever going to use it later. You won't ever absolutely throw it away. So now let's go back to this tapping chart, and let's look at this middle section here. So to tap a thread into a part, you also need to drill a hole to clear most of the material out. So the size of the hole is going to be dictated by what I talked about earlier, or what I tried to show earlier about this minor diameter. So the minor diameter of a 1032 is 151 or 152, and for aluminum, which is mostly what we're going to cut here, or cut in robotics, you want to use 75% of the thread. So if you do the math, that between 152 and 190, it's going to be 75% of that is the 159. So that's how this drill chart gets created. So you use this 159, and that 159 is a number 21. So instead of writing on the drill bit or stamping on the drill bit 159, you're gonna stamp 21. It's gonna be stamped 21. You're gonna go and find that 21 and use it to start this the tap hole. And then you put in the tap, and then you can cut the rest of the material away. Gun taps are pretty much standard. They're two flutes. They're long lead in. The tap through for tapping through holes and plates and extruded tubes. If the part is thick, you can make a blind hole. You can actually make a blind hole, which means it has a bottom. It's not all the way through. But when you do that, you really need to use a bottom tool, a bottom tap to finish that last thread. Because what's going to happen is if you try to keep that gun tap in there, it's going to bottom out and it's going to break. You definitely want to avoid breaking taps. So let's look at this again. For 3 different screw sizes, an 832, a 1032, and a 1/4 20, we only need to have actually 5 screw sizes, because this number 7 that we use for tapping a 1/4 20 is the same number 7 you're going to have around to create that 1032 clearance hole. So it's a really good reason another good reason to standardize these hole sizes. And if you actually have a large fractional drill bit set, you can use the 1364. It's really close. This number 29, a 136 is very close to a 532nd. So for 3 screw sizes, we only need 5 drill sizes for tapping and clearance holes. Order all 5 of these. Order lots of them. You're going to go through a lot of them. So how to tap a threaded hole? Look up the correct tap drill size on the chart. Drill the hole. Follow the previous steps of drilling a hole. Use a tap handle or drill you can put them in a drill. I recommend it if you're doing thin, only if you're going through thin material like a thin plate or a thin tube, and use plenty of lubrication. Keep that tap perpendicular. The ways that we do it is you have a spotter. So say you're looking in this perspective, you always have someone on the side to tell you if it's up and down, perpendicular. Another thing you can use is a tapping block. I hear Code Orange actually uses that often. And again, plenty of lubrication, the Tap Magic and WD-40 if you don't have anything else around. Clear those chips out often. Back it out, and don't ever try to don't ever try to overpower that tap. If it feels too tight, back it out, check for any issues, or risk breaking that tap. Because if you break that tap, it's real difficult to remove. It's not impossible, but you just want to avoid it. And you break a tap that's totally usable for later, and you may not have any more taps around. So, machine nuts. At a real basic level, machine nuts are just like small plates with threaded holes, and they're already tapped and easily replaceable. So, you know, it's really easy. It's really, you think it's really helpful to use instead of having to tap lots of parts. So, you know, I'm not against nuts. You can use them for high strength areas. Nylocks are actually having nylocks offers a really big advantage. You can use them when you have thin wall parts. For, you know, as a 16th wall plate, you wouldn't ever think about tapping a 16th wall for a 32 thread, and you might sometimes you want to avoid having to tap into plastic. It's not. I'm not saying it's impossible to tap into plastic, but there's often a lot of good reason not to tap into plastic at times. But when you think about how to use a tap or use a nut, you have to consider how we do it on our robots. You have to consider the fastener length. So it has to go all the way through the tube has to go through all the way to the tube and the thickness of the tube. And then you have to worry about having tool access. So your wrench or your socket, you have to start designing around that. Whereas all you need to worry about on a tap screw is having just the driver being able to drive it in. And a little more engineering principle here is that if you look at this, when you have when you use a nut and bolt here, you actually have two plates now that have clearance that are necessary, that I talked about being necessary earlier, but now you start to have a little bit too much clearance. You have 2 times the clearance for a normal hole. So then it starts to get a little bit more sloppier. And then you probably want to consider other means to precision align those holes. So rivets. Compared to screws, they're cheap, they're lightweight, they don't require threads or nuts. You can just drill the same size drill on both parts, and you're good to go. Whether they're stainless steel or whether they're aluminum, they're still going to be weaker. And so because it's a weaker fastener, you definitely want to put more rivets on a typical part than you would if you just use a screw or aim in on a nut and bolt. But they're easy to fabricate, 2 holes in a thin sheet of metal, easy to drill, and when they do wear out, or you can easily replace them. Just keep in mind the reason why you would want to replace them is because they weaken over use. Because how it works is you have this stem here, and you push it through the hole. You push the rivet through the hole, through both holes, and then you take the tool, and right here it's going to pull. It's going to pull on this stem here, and it's actually going to pull away on the material here and deform this whole area so that it makes it larger than the hole from the blind side. That's why they call it blind rivets. And then at the point that it's fully deformed, it'll pop off, and that's again pop rivet. So you get a nice little bump around here, but that's not forever. You can't really rework this. You can't tighten it back up. You can't take it out and replace the nut. It'll weaken as it gets used. So really, if you're going to use rivets, consider a replacement schedule or a check. Tons of broken rivets on the field after every match. And then there's standard drill sizes. You use a 5/32 or a 3/16 or a 1/8. But the problem is, it's very easy to leave this to swap out the size, put it on a table, and not put it back, and then it gets lost. They're really tiny. Don't lose these. Make it a habit to, once you take it off using the tool, put it right back. That's why every rivet gun has a place for each one of them. So we've talked about fasteners, we've talked about tapping holes, we've talked about nuts, we've talked about rivets. So which one would you use? And I can't say it, there's no blanket statement for this. The use of a rivet versus nut or a hole tapping is highly dependent on your design choice, your load requirements, the material availability, and your fabrication resources, whether you just have a drill press or a CNC machine. But let's go over some examples of how you would actually design this particular vacuum climber. So let's look at this area right here. So if we wanted to put two plates together to sandwich the tube, very easy to do with rivets. You just make those holes and you pop those rivets, and you can use it with really lightweight thin walls. You can do pretty much the same thing with thin walls and bolts and nuts. So if you don't have a pop riveter, and you can just use the same thing with bolts and nuts here. Now, if you needed a little extra strength here, you could actually thread the other side of the plate. So now you don't have a nut here. You can thread all the way across. And then if you have a thicker wall here, you can just tap the walls of the tube, and it's commonly done. And let me skip back over. And it's commonly done here. And so now you can actually have a thicker tube and a thinner plate. What's best? All these examples are okay. Each one of these could be further optimized for sure. Like on this example, okay, we needed a larger tube to accommodate the weight of the robot. Well, then we can lightweight it without losing a lot of strength. And that's going into an engineering principle. That's way beyond the scope of this. So that's my last slide. Let's see if there's questions here.
Yeah, we do have a couple questions from the chat. I will read a couple of them out. From earlier in the presentation, I think when you were talking about screw hole clearance sizes, Fernando asks, what's the difference between a number diameter and a fraction diameter? I believe he was referring to quarter 20s versus number 10s. And
right. I mean, yeah. It just seems to stop after the screw sizes are very standardized. So our 10 would just is instead of saying 190, and you just say 10, right? And if you wanted to go smaller size, you can't. There's not every infinite numbers of screw sizes. So they're very standardized in terms of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12, and it stops at 12 because at that point, then fractional sizes make sense. So you really want to focus on the decimal equivalent, but you wouldn't ever. I don't say I need a 190 32 unless I'm making an engineering drawing for work, and that's a different story. So that's why there's numbers, and that's why there's fractions.
Okay. We also have. Let me see. Eli asks, if you need a bolt larger than a quarter 20, what size or sizes would you recommend? Someone else in chat did recommend a 3/8 as well. So you have that for your information.
Sure, but there's also a 5/16, and then there's also 9/16. I mean, it really just depends on how big you're really going. I mean, an eighth of an inch, a half inch bolt. I don't know. I couldn't imagine where we would need that on an FRC robot. It's so strong. That's where I'm kind of saying is that a quarter 20, man, a quarter 20 of the strength of a quarter 20 is so strong that you don't want to overdo it with these.
Okay, and then there was also a question that if you have to go larger than that quarter 20, which obviously you said doesn't normally happen on an FRC robot, what thread size would be recommended? Higher thread density or lower thread density? Oh,
I mean, for a larger screw thread, yeah, you start to get more into the coarse, and you've kind of noticed here. I didn't really talk into why are there 32, 32, 32, but for a 632, it's coarse, and an 832 is also coarse, but then a 1032 is also fine, is now fine. This gets into a much larger, much more technical definition of why and how in terms of strength. Honestly, if you're going larger than a quarter inch, you probably want to start looking into the coarser threads. That's why the quarter 20. I would recommend a quarter 20 is a lot more common than a quarter 28. Not that the quarter 28 is impossible to use, but the tap size of a quarter 20 is actually a lot more easier to use than the tap size of a quarter 28. It's really too extra fine. When the threads get really fine and small, then that's when you start to want to use opposite. When the threads get really fine for being large, you kind of want to avoid those fine threads.
That sounds great. Jacob from Code Orange asked, what drill and tap chart do you use? And we can tell he's from Code Orange by his wonderful profile picture of one of their last robots.
So, I mean, there's a tap chart in every shop, and you're going to see a tap chart just like this in almost every shop. But the point is that you can use any tap chart. These names might, these descriptions might be different, but just know that if you only standardize these screws, you only have to use 3 different sizes here. Or 3 different sizes on the tap size, especially if you're using aluminum. So really, they're all going to be the same because they're all based off of a mathematical standard and the machine design handbook. And there's proofs for all these, and it's an upper level class that actually I'll admit that I dropped because I found it so boring. Because right here you have all the information already done for you.
Okay, it looks like we have 2 more questions, unless there are any more that are going to come in very soon. Todor asks, is there an easy way or rule of thumb that you can use to decide when to use various sizes of bolts or rivets?
I would say most generally just use a 1032. I mean, even though I talked about using 832s and even a 632, I could very easily argue that an 832 you could build a whole. You can just use that to build an FRC robot. Most robots aren't going to be like that. So a 1032 is so common. The hex bit is really easy to use. You can go between a button head and a cap screw really easily, and you it's just really easy to use for at a 1032. At a quarter 20, I wouldn't even recommend a quarter 20. I know the kit bot comes with a quarter 20 screw size or nut and bolt size, and I know it's easier to use, but you almost have to design around how big that screw is, how big that fastener is, and the head is, and then even the screw, the nut access. So that's why it's just kind of converged onto a 1032. It's just proven to be a really good standard screw size, and you can only bring so many screws with you, and so it's not just the screw size; it's the screw length. So now you have to have a bin of every screw length of a 1032, 832, quarter 20. So if you just try to focus and standardize your fastener size to a 1032, I think you'll be fine.
Okay, and we did have a couple more questions come in since that last answer, and a lot of them are relatively related. I'll start with our most recent one because it's sort of related to that last question. Rick asks, do you recommend threading into aluminum plate or using a steel nylock nut?
Depends on the plate. Depends on how thick that plate is. It was kind of a debate I had with a friend of mine, another mentor of mine. I worked at 968, and I'll be honest, I wouldn't have a second thought about tapping into a 1/8 wall extruded tube here. We do it all the time. I've always done it a lot of times, but if you really want to have that higher strength, you actually wanted to use that nut, and you can probably use a lot less of these fasteners. So if you have the size of it, that's okay. Then now you can just tap into it. But if you need to use less fasteners, then you can start considering using the nut. And it's also design dependent and what you can get away with, but definitely not less than a 16th, or definitely not a 16th, and 3/32 is actually what's shown right here, or 3/16 wall is what's shown here, and you can kind of see it's really chunky compared to this 1/8" wall here.
Great. And we did have another question from Rick come in. When do you use a button head versus a socket head?
That's a good question. And it's kind of funny, to be honest. It really doesn't matter. There's a technical answer to it. A button head has a lower head height, and that alone might be advantageous. But technically, the reason why it has a lower head, or what happens when you have a lower head, is that you actually have a larger surface to get enough friction. It's this slide that I kind of glossed over about friction and clamping force. But the real answer is it doesn't matter, and button heads look better. So a lot of times we use button heads, to be honest.
Great. Okay, and then we have two other questions that are very similar to each other. First one is from Angel. It asks, for a joint that needs to be strong, like on the drive base, would it be better to use bolts in a gusset or weld the joint? And I guess you could extrapolate to that to bolts or rivets in a gusset, or to weld the joint.
Look, I know teams use rivets on drive bases. It's something I wouldn't consider at our level. It's definitely doable to use bolts and rivets. Hey, top teams have done it. I know they do it. I don't think they're using aluminum rivets. So whatever stainless steel or steel rivet they're using, you need to have an appropriate driver for it. But at the end of the day, for a drive base, I go welded if you have the ability. But again, I haven't even talked about welding in terms of joining parts here. There's definitely a way we could have definitely welded these parts together as well, and that would be the ultimate strength.
Okay, and then another one on welding is from Todor again. Are there any pointers you could give on welding, when to use or not to use, etc.?
I think a drive base is really good for welding, because once you've defined that drive base, you want it held together tight, and that's a really good application of having a welded structure. Then you get outside of then you get in an FRC robot on an FRC season. Now you're talking about modularity, where you don't necessarily want to commit yourself to a certain design or a certain fabricated part that's completely welded and you can't go back onto. So after the drive base, I'd be totally I wouldn't consider too many other things being welded, except unless you're doing a situation like, I wasn't on the team at the time, but 309 when back in 2018 or Power Up, they had the Falcon Door climbers, the two buddy climbers. They had to weld that chassis because of the loads that they had to consider. So I understand that for sure. And so it really is design dependent. I'm a lot on our team. We have a welder. We have we've trained welders, student welders, and so that's part of our training and what we have capable to us. But I know that not every team does. So I wouldn't have to go to welding either.
Great. And we have two more questions. They both relate to some aspect of riveting. The first one is from Angel again. It's, would you recommend using rivet nuts for structural purposes?
I'm glad that rivet nuts were mentioned. I was going to put a little slide or a little line right here and say, hey, I recommend rivet nuts. I don't know how that, if you were reading my mind here. So what a rivet nut is that you can actually rivet a threaded fastener here, and that would that would be the tapping. That would act like you're tapping into the plate, and now you can use a fastener to bolt it on and off very easily, and take it off on and off very easily. I do recommend it. There's definitely a use for it. You have to consider the extra space or gap that gets occurred, or countersinking, or the special rib nuts that are countersunk. But then again, like I mentioned about countersink screws, you have to consider the thickness of the plate. And at that point, then I'm not sure what you're gaining by how thin of a plate you're using. But I guess I forgot to mention that the drawback of having regular rivets is that you can't easily take parts on and off together without drilling them out and enlarging the hole. So you don't want to use rivets where you're going to take parts on and off frequently or potentially. So rib nuts allow you to do that, and yes, I'd recommend it. I didn't want to get too far into it when I had a line. I actually had that line right in here, but it's too much to explain throughout the whole, considering the breadth of the information.
Well, I'm glad we were able to touch on that. It looks like we have one last question. It's been a while since any more ones filed in. Eli again asks, do you normally use full steel rivet or aluma steel rivets with a steel mandrel and aluminum head?
I'm not the rivet expert. I quickly share that I don't really like rivets that much, so I don't have that much. Honestly, I don't have that much experience with them. But typically, they're going to be aluminum that we use on our robots. Is going to be aluminum. I think all aluminum. They pop off a lot easier, and they're just a lot easier to work with and not having the hand riveter. There is a Milwaukee M12 powered cordless riveter, and we got it last year, and it's amazing. It's amazing. Now that actually is starting to make me like rivets. I would recommend, if you guys are thinking about using rivets, throw this or put this into the lower shelf here and buy that Milwaukee M12 riveter. It's amazing. I can't recommend it enough. It's making me like rivets, but I just haven't used it that much.
Yeah, well, I certainly love a good pneumatic riveter myself. It looks like that was the last question. Thank you very much, Tyson. I'm sure all your information was extremely informative to a lot of our rookie members and teams, and I'm sure even the most expert of teams learned a little bit from this presentation. We'll be back here tomorrow with 2 more workshops for you guys. Tomorrow we have motors and gearboxes with Team 5199 at 5 p.m., and you can learn from some of our past mechanical leads about how to choose motors and gearboxes for different purposes and uses. And then at 5:45 p.m., we'll have Teams 3309 again, Code Orange again, and 5199. And that will be a panel from our Woody Flowers finalist mentors on mentoring to make a competitive team. You'll be able to learn from our Woody Flowers finalists with years of experience about how their mentorship helped grow the competitive aspect of their teams. And we're super excited to hopefully see you guys tomorrow. Thank you all for tuning in and dealing with us during our technical difficulties. Thank you for that chat suggestion. And we will see you tomorrow. Thank you all very much, and we hope to see you again.